Hey, what's going on? Okay, so yeah, welcome to my channel, and today I'm going to show you how to do style transfer from the bottom up using generative AI. So basically, when you see things, something like Dolly being able to generate images in the style of XYZ, I'm going to show you essentially how on a basic level, the style transfer mechanism works. We're not going to get too complicated here because this is just for demo purposes. But even for this demo, it should be somewhat elucidatory. Yeah, and so with that in mind, what we're going to do exactly is we're going to use two generative AI algorithms to come to compare very basic ones, which would be the basic variational autoencoder and the basic generative adversarial network. So I'm not going to go over the theory of those in this video. The theory, just a quick recap, but not such a deep dive. The variational autoencoder is basically built off of the standard autoencoder architecture, which is a neural network type, which takes in data, compresses it to a latent space, and reconstructs the data. And it's usually used for, the standard autoencoder is usually used for denoising. With the variational autoencoder, you can actually generate new images based on the input image by introducing slight variations to the output. And the variational autoencoder architecture came out before the generative adversarial network architecture, which came out about 10 years ago and was produced by Ian Goodfellow. So the generative adversarial network has a different mechanism of generating a new instance of something using generative AI. Okay, so that's the quick, and so, okay, all right, let me also just quickly mention that the generative adversarial network actually consists of two networks, an encoder and decoder network. And it's a much more involved process overall. The one network, the decoder network, attempts to fool the encoder network attempts to fool the decoder network and try to create something starting with random noise that could potentially be a real image. The discriminator network doesn't will check that thing that was generated by the initial encoder network, and it will determine whether it was real or not. And if it's not real, and by real we mean something that's in the discriminator network's training set, which, since it's a neural network, it was trained with data. If it's not real, then it discards it, and then it teaches sort of the feedback loop of the model, training loop of the model, attempts to minimize the loss between the discriminator and generator networks, so that the generator gets closer to generating real images. Okay, so now that's the very basic primer. So what we're going to do is we're going to actually take both of those algorithms, and we're going to generate some training data in the form of mazes using a traditional procedural maze generation algorithm called depth first search, which is actually good for generating mazes. And it's going to use basically depth first search through a graph using some sort of graphing nearest neighbors algorithm. It's not pretty straightforward if you've studied DFS flood fill or anything like that. But I'm just gonna go through it, and then what we're gonna do is we're gonna use one of the networks to take in those maze training data sets, and then start to output new instances of mazes. So it's basically, instead of using procedural generation to generate the mazes or a maze-like pattern, we're outputting whole new mazes. That's the goal from the generative adversarial network, or the VAE. The other thing I want to mention is that, this again is pretty straightforward, pretty simple mechanism to do so. And the more complex the style you need, the more complex the type of network that you need. So let's get started. So first we're going to import our dependencies, matplotlib, myplot, splt. Okay, we're gonna tensor. I don't have autocomplete on here, so I'm pretty sure. And I turned off generative autocomplete because I didn't think that was useful. Import model and sequential. These are the libraries for neural network. Sequential. Okay. Then tensor flow. We're going to import the various keras subpackages, layers. Import dense, which is one of the layers of the neural network. Batch normalization. Let's see what else. Batch normalization. Leaky ReLU, because we want the actual activation function. Reshape, because we're going to be converting between different network types. Reshape conv 2D transpose conv 2D to D, flatten input lambda. Let's see. Flatten input lambda. Input lambda. Okay. So these should be all my basic neural network operations. And next what we're going to do is we're going to go to the optimizer, TensorFlow keras.optimizers, import Atom. Atom is a popular choice for neural network tasks. TensorFlow let's see, keras. I think we want to import Greece. Let's see, backend as K. Okay, cool. So these are our imports. I'm just gonna run them because there's always like something going on. Flatten should have been there. Let's see. Import. This should be from. Okay. And we'll do from here. From here. All right. And let's see. Missed between reshape and conv network 2D. Pi plot. TensorFlow keras. Deploy. Always stupid stuff. Leaky ReLU. Why not? Leaky. Oh yeah, it should be E. Models back to here. Leaky ReLU. Okay, cool. The imports are there. Okay, so right now we're going to put together the actual code for this example. So the code includes first generating the training data. So the training data is just going to be a bunch of maze patterns, and we're going to use a pretty simple algorithm to generate that training data called depth first search. Yeah, so first we'll create our generate maze function, and that maze function is going to be I set a size parameter to it that's going to include the size of the maze, so the width and height in terms of pixels. So you'll see how that looks like. So we're going to first initialize our maze with an NP array of zeros. So this is just going to be a matrix, and we're going to just assign it to int as data type int 8. Okay, so we're going to start with pretty much a stack that has coordinate 1 1 on it. This will be evident if you're familiar with the DFS algorithm and the way it's used to generate mazes. You'll see how this is implemented. So we have a visited node because we need to keep track of what we visited already, so we don't go down that path. And then we have we're going to start now iterating through our stack, and we're just basically going to do something similar to like how a flood fill would be done. We're going to pretty much visit nodes, nearby neighbor nodes, but we're going to kind of choose random directions as we go through the node, as we go through each node, and we're going to put that node on the stack and then like generate a new path, go in a different direction until we get to an existing node. So this is a simple way of generating this maze, but we'll start with the cell, the first cell, and then the XY coordinates of the cell will be we'll specify as the cell object. So the maze itself, as you see above, we defined it as a NumPy array of zeros. So we're going to extract the coordinate from the stack, and when we say that maze x of y, x and y equal maze of x comma y equals 1, that's where we're defining a wall. Okay, so then neighbors. So now we're going to actually visit the nodes. So how do we visit the next or assign the neighbors? Okay, so the neighbors we're moving 2 spaces up, 2 spaces down, 2 spaces left, 2 spaces right. That's how we're going to define the neighbors. And the neighbors are just going to be we're not going to include diagonal neighbors because we don't care about diagonal walls, but that could be something for the future. But for now, we're just going to include all the possible neighbors and neighbor directions rather. So we're going to go up and left and right. That's x plus 2 and x minus 2. We're going to go in the vertical axis as well, y plus 2 and y minus 2. And so this should allow us to define the direction that the direction of all neighbors. Neighbors, that's how you spell it. Yep, okay, cool. And now what we're going to do is we're going to keep track of what our unvisited neighbors are. Okay, so we'll be able to tell what's unvisited because we'll be able to tell what's already in the array of what we've seen and what the next nodes are. So you'll see when I write out the function unvisited neighbors equal. So again, we don't have to get too wrapped up, and then we're going to say that. Well, first we'll just assign our unvisited neighbors. We don't have to get too wrapped up in how this pattern is created. This is just for the purposes of creating a pattern for a maze, but essentially this whole thing can apply in many different patterns. So this will just be a simple random-ish pattern, and it's also good for neighbors. And so if now we check if the neighbor is less than or equal to 1 to check if the neighbor is a wall or not, or like an absolute boundary of the maze. And if it's less than size minus 1, so the size of the maze, because we don't want to go outside of the bounds of the maze, so that won't be a valid neighbor. And we do that in both the horizontal and vertical directions. And we find that we check if the neighbor is in the visited or non-visited category by looking in the visited array or visited set. Okay, because this is how we're keeping track of what we visited already to generate the maze. Okay, so now that we have our unvisited neighbors, we need to see if something is in the category unvisited neighbors. Unvisited neighbors. If unvisited neighbors, okay, then what we're going to do is we're going to go to the next cell. Now we'll pick a next cell. We have to check, how do we know if it's, we are now able to get the unvisited neighbors. That's the whole category. We are able to find all the neighbors, but unvisited means whatever's not in the visited set we created. And that visited set's initially going to have only one point in it, which is the initial point, which is going to be the visited point, the first visited point, which is kind of the seed of the maze. We could also specify this to be a different value, but for now we'll just keep it simple. So the next cell equals unvisited neighbors. Okay, so we're going to now pick a random direction. Randint. So this is, we're going to start with, and the random direction is going to be, we're going to just initialize it and have it within the value of whatever we already have unvisited, because other than that we're not going to like have extra things that we don't need here. So this is going to be unvisited neighbors. Okay, and so once we are able to find the next unvisited neighbor set, then we append the next cell to the stack. Okay, the stack is, we're essentially, in order to traverse the maze and create walls, we I'm eating some chips. We go through our stack and pop the next element off the stack in order to find the next traversable directions. Again, visit the DFS flood fill if you have any questions about this. It will make more sense. But so once we once we append the next cell to the stack, we visit it. And then, in order to be able to then decide, like, okay, now where in the maze we are, okay, we're going to take the cell of 0 plus next cell of 0. And I'm going to plot these mazes out, these generated mazes out, to prove that these mazes do exist. Okay, now what we're doing is we're taking, not maze, max. We are taking here. Now we're going to pick the next possible directions in the, we've already picked the next possible directions. We're just going to then fill out the value of the next wall. That's why we're setting this to 1. Then maze next cell, okay? And we're getting these next cell values. Remember, we've already got these values essentially. We're just getting the next cell values, the X and Y direction. And next cell is going to be, again, we're always picking an unvisited neighbor here, right? So this is just the next wall that we set. Okay, and then else if we, now this is if we are essentially in the unvisited neighbors realm. Then if we're not, then we can remove this from the stack. Okay, so we pop off the last element of the stack, and then we return maze. Okay, so this is probably not going to do anything right now, but we'll run this just to make sure. Oh, I probably should run everything here first. Okay, I'm just going to run this. It's going to take a second to run. And so while that's running, I'm going to then write the code to actually plot these out to the screen. So we plot our mazes like so. So basically we're just doing an image plot. And that just is just like we're treating each of the maze sections as a block, right, on an image pixel, quote unquote, or a group of pixels. Okay, so so we're gonna have 3 plots because I'm gonna plot 9 by 9 here. Okay, I'm gonna put just 9 examples, but there can be many. We're gonna generate more examples. This is just for the initial training data. Plot, subplots, and so we're gonna have, again, 9 by 9 square, fig size equals size. Okay. Okay, so for, sorry, there's noise in the background, but now once we create our axis, we're gonna go through each axis for I, comma, AX, and we're gonna enumerate these together. Then we're going to do, on each axis we're going to show one of the mazes. I always type this wrong. We're going to also put it in grayscale because these are just going to be black and white, so no need for RGB or anything like that. But if you use a different pattern other than a maze pattern, you would probably use an RGB pattern, or like in all likelihood. So yeah, you can change that as needed, but we just have ones and zeros for now. And so what we do is we plot, now we're just gonna add a title and plt.show. I'm gonna pass the title in. Okay, so let's see. All right, that should have printed something. Let's see, what did we fail? Return maze. Indentation. Size. Let's see. I did not forget a comma. Oh yeah, I did forget a comma. I hate when that happens. Okay, great. So this code looked like it ran, I guess. And our stack is defined right here. Stack, we're going to actually, sorry, this should be equal to like that. And we should have, oh, we gotta import numpy mp. Okay, so we'll just put this import here, make it easy for ourselves. Not have to run the TensorFlow imports again. Doesn't make too much of a difference. Okay, cool. So that should take care of everything. Visited. Okay. Once again. Okay, cool. All right. So now we have our plotting function. We'll run that in a bit, but before we do that, I want to actually write the code for the machine learning part. So don't worry too much about this now. I'm going to write out a few functions. The sampling function is going to be the function I use to initialize the noise data on the variational autoencoder. As I mentioned before, that's going to be one of the models that we use. And then we could probably use other we will definitely use the generative adversarial network. Both of these, and we're going to use the probably the most basic version. But k.shape. Okay. Again, don't worry too much about the specifics here. What basically I'm doing is creating the noise parameters. And the noise parameter is going to help us define the initial starting noise. And that's important because right now we're going to start with random noise and we're going to work our way down. We're going to refine the noise into an actual prediction. Epsilon. There's also many ways of doing this. Epsilon. And I'm using the parameters from the typical noise parameters for the sampling output. Random. I'll put some examples in the chat on how I define these later and why. This is just to kind of get the ball rolling. And return z-mean. And okay, so this is going to be, again, just a noise term. And we're using the exponential function to essentially keep track of this, or to generate this term, rather, z log var. And this should be epsilon. Okay, again, there's other ways to do this. You need to do this like this, but this is just one way to do this, so we can epsilon. Okay. So now our variational autoencoder, we're going to we're going to put it in a class, VAE, variational autoencoder. And so we're going to use everything that we did before to output the autoencoder variables, and we're going to pass to it the input shape, which is the shape of the maze, and the color channel, which is going to be just 1 because we are only using the grayscale. And so we're going to also pass the latent dim. So the latent dimension is where the autoencoder compresses the data into, the space that it compresses it into. So this is based on the standard autoencoder mechanics. So some of the assumption here is that you've already seen what an autoencoder looks like and does, and if you haven't, I have another video which will give you that information, which I'll put in the comments. I'll put in the description. Now, I'm just assigning these to member variables. The latent dimension equals the latent dimension. So this concept of latent dimension, again, it's kind of the interior space of the neural network architecture where the actual training is compressed, has molded the weights. You can put it that way. And so inputs equals, so now we're going to create input, so we can input this into the neural network for training. So this is going to be a little more complicated than the standard autoencoder, because the standard autoencoder is not going to use the variational part. So in the variational part, we're going to use this mean and sampling value to get the actual variational parameters. And we're going to obtain that from the decoder. So we haven't defined the decoder function yet, or the encoder and decoder function yet, but we'll do that in a bit. Inputs, latent dim, that should be fine. Latent dim, I don't know, maybe it needs to be updated. Okay, and so again, don't worry too much about this, the specifics here. This is just going to be how we are going to be defining the layers of the neural network. Okay, there's different ways to do this in PyTorch, Keras, etc. So latent dim, and z mean. Again, these are the explanations here are a little beyond the whole weeds, but we can go into the specifics. Right now, I'm just going to focus on the maze generation part. So the latent dim is defined. It's passed in as a parameter. Input shape equals, that's probably the reason. Yep, I knew it. Okay, I knew it. And so now we have our encoder. Now we have to actually build our decoder. So once we have the layers of the network, which are defined above, they will do some work, including being trained. Build decoder. Okay. So, and now we will actually define our loss function. Now that we have our network, we have to know how to use backpropagation on it. And recall, for those who don't remember, backpropagation is the algorithm that the neural network uses to actually do its work. So what we're doing here is going to define the loss function. In this case, we're going to be using a loss function called binary cross entropy. There's other loss functions we could use. They have different uses for different cases. Sometimes mean square error is good, sometimes this is good, but for our case, it should be sufficient. F dot. So now we're going to condition the outputs a little bit, so and inputs, so we can make things easier to deal with later. Okay, cool. So this should outputs. Okay, so now we have our inputs and outputs flattened, and we're going to now compute our reconstruction loss per step. And equals np.prod input shape. Okay. Then we're going to do we're going to use the Kolbeck-Leibler loss, which is a typical loss metric we're going to use. It's actually not really a metric, but it's used for variational autoencoders to kind of determine how close the probability space of the encoder is to how close the probability spaces of the input distribution and the training distribution are. We'll leave it at that. And so this is just an expression for the loss, the Kolbeck-Leibler divergence, z log var. And so let's see. Then KL loss equals KL sum, KL loss and axis 1, because we're going to play this to only one axis of data. So KL loss, KL1, K sum, a lot of KLs, and finally we're going to have a final term here, corrective term, if you will, negative 0.5. Okay, and so now we're going to, this should be the other way around, times equals. Okay, and finally we're going to compute the final VAE loss after we've defined our loss expressions. We can actually put our loss expressions somewhere neater to make them more easier to manage. Reconstruction loss plus KL loss. Okay, these are both losses, like distributional related losses. And okay, rest construction. That's to be reconstruction. Okay, cool. And then we're going to append the loss function to the model. Loss VAE loss, and self the model the compile optimizer equals atom. Okay, because we're using the atom optimizer for back propagation and for adjusting the weights. Cool. So that looks like we have everything. VAE loss. Binary cross entropy should be defined. I'm not sure why it's not coming out. Okay, now we're going to get to the so-called fun part. Right, now that we have our VA class, we can actually build a decoder, and now this is where the actual structure or neural network architecture comes into play. We're going to build the encoder, and we've invoked the encoder above. So inputs equals the input layer shape dot equals self dot input shape. That's just how we define the shape of the maze and other things, but yeah, this should self. Okay. And then we're just going to create a layer. We're going to create dense layers. Flatten inputs, because we're sending image data in, so we're going to encode it by flattening it first, and then, so that means turning it into a line, right? And in 256, now we're defining the 256 node dense layer equals, and putting an activation function relu. You can, again, use the activation functions, which are useful. Leaky relu prevents a problem called exploding gradient from occurring, or vanishing gradient, actually. And so that's a little out of the scope of what we're doing, but like I'm just letting you know that you can use other loss functions here. Then self.latent dim name. Okay, so okay, so the dense layer is going to be, we already have our dense layer, so we're defining another dense layer. And you might be wondering, how many layers do we need? Well, we're just going to define a simple autoencoder, a variational autoencoder now, with a dense interior layer. And equals dense self latent dim. Okay. Name equals z log var. Okay. All right. So now we've specified a few more things here. Okay. And finally, we're going to return the model. I'm going to move my face out of the way here. We're going to return the actual model. Return model inputs. And again, this z-mean and z-log-var are just one way of defining this for the variational autoencoder. And the name is encoder. Name equals encoder. It requests a name. Simple. Probably for tracking and other purposes too. So that's our encoder. Now what we want to do is we want to build a decoder. The decoder itself is easier than the encoder. Again, the decoder is not using special decoding mechanics, but and we're going to space latent inputs equals input shape equals self dot what do we want to do? Latent dim. Okay, self dot latent dim. So that should just define the initial input. Then equals np.prod. We're now getting the images. Self.input shape. Again, activation value, because everybody does that. Value. Okay, and we're almost done with this part here. A lot of stuff going on. Okay, and so I'm going to reshape the network inputs. Input. So that we can pass it over to our conv2d transpose, which is how we're going to be building the variational autoencoder decoder. Okay, using this convolutional neural network. Shape. Okay, cool. And so here's where we specify conv2d. What is it? Transpose? Do we want the transpose? I think we do. Yeah, we'll go with that. It's a matter of like matching up the dimensions too and the results and the input. And so now we're going to choose a different activation function called sigmoid. So you've seen the sigmoid function. It looks like an S-shaped curve if you haven't seen it before. That S-shaped curve is used in all different applications. But for me, there's some discrepancies about it. Okay. Now we have our outputs, we have our inputs, and now all we have to do is just return the model itself that we created. We're creating latent inputs, outputs, decoder. Okay, cool. Return model. And now we're gonna have to train this bad boy. Okay, def train self, and this is gonna get called later because we're just putting all the training and stuff into one function, which is probably a best practice. No, definitely, yeah. Okay, and then we're gonna start batch size. Batch size is a little complicated to explain too, but just think about it as the rate at which data is flowing through the network and being trained in a single step from layer to layer. In a batch, or is it less batched out? So anyway, that's as far as I'm going to go there. Epochs equals 200. And so model fit. And so now this is the training is just using the fit function that comes with standard at this point with pretty much any machine learning model that we use. Batch. I always say batch. And then what epochs? Epochs equals epochs. Yep. And then we can maintain. This is actually pretty good if we want to have something that shuts off automatically. Okay. So we're almost done with this. A little more to go. Okay. So what we're going to do is, now that we have to do one more thing geometrically speaking, and we have to do what's called thresholding. You'll see why. I'm just going to write the function here, and I'll demonstrate what happens when you don't use thresholding. Oh no, here we go. I didn't want to run that. Okay. Images array equals NP. Let's see what I want to do here. I'm going to put images, array images, and then we're going to, for each pixel where the image in the image array is greater than the threshold being 0.5, set to 1. If it's less, set to 0. You'll see exactly again why I'm doing this. Images array greater than 0.5, 1, and 0. Okay, cool. So now we have that. Finally, now that we have our thresholding routines established, and I'm just going to pull this out here of the function, then finally, we get to the actual training execution part, where we just training mazes, training mazes, and we have a generate maze function, generate maze. Okay. We're in range 9. Okay. So we're going to go through all the 9 mazes again, because that's what we did the first time. That's how I intended to set up. You don't have to set up your project that way exactly. But again, I wanted to just do that for illustrative purposes. And we're going to use our handy, let's see, do we even have it here? Yep, we have a handy plot mazes function. Plot mazes. And we send in training mazes. Training mazes. What's a good name? From DFS. Okay, cool. Awesome. And then finally, in the home stretch, train equals np.array. training mazes. Again, we're reshaping the input to be something that we can work with visualizations on. These are not always difficult tasks. Reshape. And so, if the mazes get wrong, out of hand, etc., there's always this, which I don't think is going to happen. Anyway, okay, cool. So your reshape setup, and we need to just close it all out, I believe. Okay, cool. Oh, did I miss something? Okay. I think that's right. Okay, let's see. So now that we are able to reshape our array, this should be 1. And now it should be that. Okay. And oh yeah, just keep that as a tuple. Okay, cool. Now all we need to do is actually plot our stuff. So model type, we're going to say model type equals GAN, do one thing for generative adversarial networks, and model type either I'll code it equal autoencoder, in which case you do a different thing. All right, so we'll start with, and if model type, also as you can see there's more customization on the variational autoencoder, so you could probably customize that to get better results, but I digress. So equals GAN, we're going to say how the parentheses too. Sorry, I'm yawning a little bit. It's late here. GAN equals GAN dot pre-trained. Okay, so now we're going to actually train. Now we're going to execute the training loop. We'll do it for 200 epochs, but you'll see quickly how that doesn't always help. 32 and models equals GAN. Now I'm creating the generator and adversarial networks, and so so that's important because let's see. All right. Okay, and so elif, I think, yeah, it's elif model types equals VAE. We're going to use the VAE we saw there. Okay, so model type equals VAE, then we're just gonna, we already have the VAE constructed, so that's the easy part. VAE, that was also a little tiring. VAE, and then train x, train batch size equals 32. Good. Okay, cool. Then we're going to pass in epochs again. Okay, cool. And now, last type of code I'm going to show you today is that we're going to plot the generate mazes. Generate mazes. Generated, we'll call it generated mazes, equals model.predict, because we're going to use the predict function on the model. Random normal 0 1 1 okay. see. Yeah, so basically this is our prediction function. There's a lot more here to it. Okay, so now this is just essentially a reshaping of the entire area, it looks like. So yeah. Okay, so you know what, I'm going to continue this here. If model type, I was just looking for a better way to space these, but this is fine for now. And else, else model dot predict, and we're going to actually use the GAN to do the predictions in the GAN case. And p dot random, almost get random 0, and so let's just say we're going to okay. All right, where was I? When something's so many lines, I know there's a lot of lines here. I'll try to clean this up, but you get like some weird form of highway hypnosis. You know what I mean? Train dot shape 0 and 1. 1 paren bracket and paren again. Oh yeah, I know this is tedious, guys, but this is what we have to do. Then let's see. All right. Okay. After just flatten section 0. So much like a okay, for okay, cool. And that should be it for that. And so let's see first plot mazes. I'm gonna say generated mazes. And generated mazes by neural networks. Okay, so this should be interesting. I don't have no idea if this is gonna work. Of course. Where did it fail? Oh, yes. Okay, slight hiccup, but we're back. Okay, so, all right, so now our GAN model, we're going to use the Variational Auto-Encoder model. We can compare that. So I ran this, and you see I have my test data here, which looks like real mazes, but then this is what came out, the neural network generated. So it didn't quite learn the same pattern. So we can actually improve the pattern more so by increasing the number of epochs and the training intensity. So let's change the number of epochs to 300 and the batch size to 64. And we'll see that this, okay, starting to look more maze-like. We're going to change the epochs to 500. We lost something here. Let's try the batch size to 128. Yeah, see, you can tell this is not exact science all the time. Okay, well, you know, perhaps better, perhaps not. We're going to try 800 epochs worth of training, and let's see how that gets us. So looking a little better. Anyway, the idea is the pattern is roughly becoming more and more advanced. So we're going to try 1200. And generally what you can see from this so far is that like the maze pattern looks more repeatable the higher the parameters that we get are. So again, but you see like again it just generates different slight variations of the maze. So let's try now we have a huge batch size, and I think that's starting to look more maze-like. Okay, so again, you can play around with this. The point is, this maze style is now replicated here, and you can do that with several other styles. I'm not using a maze. The data set was generated using a maze algorithm, but the neural network learned the pattern from the input data and was able to produce an output. Okay, so that's the key thing here. We want to emphasize that the neural network doesn't know what a maze is underneath the hood. Okay, so yeah, and if you have any other questions, I think then we'll talk about that later. But that's basically what maze generation is. We can also do things like increase the size of the mazes as well. If I have size 18, for instance, let's try 22. I think I'll have to change a few more things to size 20. Yeah, I'm going to have to change 18 to 22. I can just generate a maze size overall here to account for that. Oops, there's more. Where else do I have to change? Yeah. 22, 1. And so again, as the maze gets bigger, and so yeah, so the patterns will now increase accordingly. Okay. Yeah. Cool. So any more questions? We'll go over that at another point. But in the meantime, happy coding, and like, subscribe if you like my content. See ya.